Okay, so today we're going to talk about tangents, velocities, and other rates of change. And a couple of nice results of this section have to mainly do with uh, that tangents, velocities, and other rates of change. It's practically, we're doing the same thing over and over and over. So you'll notice as we're going through these notes, and when I define these tangents, velocities, and other rates of change, I'm pretty much rewriting the same thing over and over. So it's just there's some minor differences between the two. Like for example, there will be certain cases where tangents ends up being velocities, but tangents aren't always velocities, and so on. And the other comment I want to make is that we kind of did this in section one, except we're going to find a more efficient way of finding these. So practically after today, you can disregard section one because this is practically doing the same thing as section one. Okay, so let's kind of do a little bit of review as to tangents. So here's what we know. In section one, we learned how to find slopes of tangents without using limits. And if you remember, we weren't using limits. Instead, we were using a table, and then we saw that what value that our table, as we got closer to a specified value, what y value our function approached, and that was pretty much our tangent line. So if you remember, it was kind of like a secant line, and then the slope of the secant line slowly became the slope of the tangent line. So if you don't remember it, no worries. I'm going to give you another picture that kind of shows what's going on. But let's define officially how we'll find the tangent line of a curve, and of course how we'd find the slope. So by definition, the tangent line to the curve y equals to f of x at the point P, which is found a comma f of a. So notice, of course, what we know is the line that we're talking about that's tangent obviously has to be tangent to a curve. And if it's tangent to a curve, that means the tangent line and the curve share a point. And we're saying the point that they share is a comma f of a, which what does that mean? Of course, the x value of the function will be the same x value as the tangent line. And then what do I know? How do I find the y value of this line which is shared with that function? I just plug in a into this function. So this point is practically the point of tangency that we're dealing with. So this line goes through the point, and that point is also on this function. So this is the line through P with slope m equals to the limit as x approaches a of the following: f of x minus f of a over x minus a. And of course, it's provided that this limit exists. Okay, so let's talk about kind of visually as to what's going on. And see, this notation you've seen in analysis. Okay, now we're going to take a different approach to this notation, which is going to be equivalent, but it's something else that we're going to use more commonly. But let's see what's going on as far as visually, how this is represented as the slope of the tangent line. So what you notice is that our point of interest is what? It's at a comma f of a. So that means my x value at that point of interest is a. So in other words, if let's say I am, and let's leave this up here so you could see it, but what's happening here is that, think of it this way. if I want to find, if I have a curve that looks like this, for instance, and my goal is to find the slope of this tangent here, okay, this tangent line. And of course, this point has coordinates what? A, that point has coordinates a comma f of a. So we could find this point, no problem. But to find the slope of this tangent line, the problem right now is I need a second point on the tangent line to find the slope of this tangent line. Unfortunately, I don't have that, okay? So, and I don't have any other information about that line other than that line shares this point with the curve. So what we're doing is we're saying, look, pick any x value. So let's say, let's call this x1, for instance. And what we're doing is we're now finding the average rate of change, which, because if you think about it, this is the average rate of change, isn't it? We're finding the average rate of change from this point to that point. And if I were to draw that out, what do we get? We get the slope of that line, which clearly the slope of the red line is nowhere near the slope of the tangent line. But what are we doing? What is this saying? As x, the limit as x approaches a. So what I want to do is with this x, I want to get this x closer and closer to a. And as x gets closer and closer to a, we'll notice that something happens to the slope of the secant line. So then let's pick a point even closer. So let's call this, I don't know, x2, which is a little closer. So this point, which is on that curve. So if I draw this line out, notice how the second slope got even closer to the slope of the tangent line. And if I get even closer, so let's say if this is x sub 3, we get this point, which is basically, that's the line. And of course, the slope of the secant got even closer to the tangent. And I think by now you could see what's happening. See, if I go even closer, like x sub 4, and if I draw that line, it's not exactly the same as the slope of the tangent, but you could see it's starting to run pretty much these lines, as x gets closer to a, the slopes of the secant become the slope of the tangent. So basically that's what this is doing. It's saying, look, f of x, for example, that's f of x minus f of a, which is the rise. And then the x minus a is the run. So what's happening here is that as these points get closer and closer to the point of tangency, the slope of the secant gets closer and closer to the slope of the tangent. So in other words, this right here gives us the slope of the tangent. And if you remember, we did this in section 1, except we didn't solve it in terms of limits. We made a table, but in section 2 and later sections, we've learned that, hey, there's ways we could evaluate a limit without having to make a table. So what we're going to notice is this is a much more efficient way of finding the slope of the tangents. Okay. Now, another way we could write this, so basically the definition I just gave you, which gave you the slope of the tangent, this is equivalently, which I'm going to use this notation over the original one. Okay. The slope of the tangent is the same thing as the limit as h approaches 0 of f of a plus h minus f of a all over h. Okay, so this also gives us what? The slope of the tangent at x equals a. So the picture shouldn't change. So visually speaking, how does this slightly look different, or the notation looks different, but it's still the same thing as the picture I drew out earlier for you. So if you think about it, if I were to grab the same graph, and let's say this is a, and my goal is to find the slope of this tangent, which is practically what we did earlier on with the other notation, But what's happening? So h is now some distance away from a. So think of it this way. If I call this distance h, what's this x value? This x value becomes a plus h. So f of a plus h is what? The y value at f of a plus h, at a plus h. F of a is the y value at a. So if you say f of a plus h minus f of a, that just gives you the rise from a to a plus h. And of course, what's h? H is basically the run. So if you think about it, f of a plus h minus f of a all over h, that just gives you the slope of this secant. And sure enough, as h goes closer and closer to 0, that means the distance between a plus h and a is decreasing. So this point is getting closer and closer to that point. And what does that mean? The slope of the secant is going to start approaching the slope of the tangent. So this does the same thing as the following: limit as x approaches a of f of x minus f of a over x minus a. This and this mean the same thing. This one is just more commonly used in calculus books as opposed to this one. Okay, so I'm going to stick to using this to find the slope of the tangent line, and you'll notice that that's basically something we're going to use over and over and over. Okay, so for these, we can make a comment is that, look, so this picture above, we could say, look, notice as h goes to 0, the slope of the secant approaches the slope of tangent line. And so that's kind of like the main idea as to what we're going to be doing. Okay, so we'll do a couple of examples in a minute. All right, in fact, let's actually do our first example. So for example 1, we'd say find an equation of the tangent line to the curve y equals to 1 plus 2x minus x cubed at the point 1, 2. Okay, so the first thing we need to do is, see, we know that the point the tangent line goes through, which is this. So if you think about it, if I want to find the equation of the tangent line, what I need to do is I first need to find the slope of the tangent line, and I need a point on the tangent line, which the good news is we already have a point on the tangent line. So all we really need is the slope. So we need the slope of the tangent line. And if you remember, at what was it? At a equals to, a is practically our x value, at a equals to 1. If you think about the definition of finding the slope of the tangent line, it was this: limit as h approaches 0 of f of a plus h minus f of a all over h. And so what's a represent? A represents the x value that we're interested in finding the slope of the tangent line. If we come back to this picture, see, what am I trying to do? I'm trying to find the slope of the tangent line at a comma f of a. So notice how this f of a plus h is just a distance that's approaching 0. So we're not concerned about h, but a is pretty much the x coordinate of the point of tangency. So in this problem, if you look at it, technically speaking, just basing it off of this definition, that's my a. Okay, so what I want you to do real quick is take a minute and see if you could set this up, and then see if you could simplify it and see if this limit exists. If this limit exists, that will basically be the slope of the tangent line. So go ahead and take a minute and do that real quick. All right, so if you had basically paused it and you worked it out, here's what you should have gotten out of this. So for this, what you get is limit as h approaches 0 of f of 1 plus h minus f of 1 all over h, which what does that become? That becomes the limit as h approaches 0. And by the way, maybe I should do this here. I should put m tangent. So this is basically what the slope of the tangent is, okay? So this is the limit as h approaches 0 of what's 1 plus h? Well, grab this, and this is my function. And in place of x, replace it with 1 plus h. So what do I get? I get 1 plus 2 times 1 plus h minus 1 plus h cubed. So that's what this is, okay? Minus f of 1. Well, what is it that we know? F of 1 is actually 2, okay? All over h. So what I want to do now is I want to simplify this and see what's our goal. I think by now we're pretty good with solving limits. My goal is to eliminate this h. If I could eliminate that h, then I could use direct substitution and I could finish this off. Okay, so let's see what happens here. A bunch of things should cancel out. I really don't want to multiply this out. So I'm going to avoid doing that unless I'm forced to cube this out. So I'm going to try to see if I could work backwards and somehow factor this, okay? So here's what I know I can do. I know that I could distribute this 2, and let's see what happens here. I think I might have to just multiply this whole thing out. I don't think this is going to work out, but I'm trying to see. Actually, we might be able to. So let's see what happens here. It's all about how you manipulate it. Now, if you don't see this, you could just multiply things out. It's going to be, it might take you a little bit of time. So what do I have here? I'm going to leave this 2 times 1 plus h alone, but I could add that 1 to the negative 2. And so what do I get? I get 2 times 1 plus h minus 1 plus h cubed, and I get minus 1 all over h. Okay, so I'm actually going to do this the long way just so I don't want to confuse any one of you guys, but here's the shortcut, and I'm sure if you could follow along with the shortcut, you could use the shortcut to try to avoid having to multiply these out. But what you could do is you could factor out a negative from these two terms, and then notice how you're going to get a 1 plus h cubed plus 1. And if you remember, there's a sum of cubes formula that you could use to factor, and that would be a quicker way to factor this, which would keep you from having to multiply it. But just to make sure that we all follow along, I'm just going to do this the long way. If you want, you could ask me in class, and we could do the shorter way together, just so you see it. But here's what we have. If I distribute the 2, I get what? 2 plus 2h minus, if I cube the 1 plus h, let me just do the work off to the side. So what do I know? 1 plus h times 1 plus h, that'll be just 1 plus 2h plus h squared. And I want to multiply another 1 plus h to this, so it'll be cubed. And if I distribute it, what do I get? I get 1 plus 2h plus h squared plus another h plus 2h squared plus h cubed. So if I put that here, what does that give me? I get 1, and then I have 2h and an h here, so that'll be a plus 3h. And then what do I have? I have a plus 3h squared, and I have a plus h cubed. And there's a minus 1 here, all over h. So then let's distribute this negative and combine all like terms. And hopefully, I should have everything in terms of h in the numerator, so I could cancel something out here. So what do I get here? I get 2 plus 2h minus 1 minus 3h minus 3h squared minus h cubed minus 1 all over h. So let's see what happens here. Minus 1 plus minus 1 is negative 2, plus that 2, they cancel out, which is good. So these 3 are gone. And then what could I do here? Now we can just combine like terms. Limit as h goes to 0. So 2h minus 3h is negative h. And then I have minus 3h squared minus h cubed all over h. And then you could factor out an h from the numerator. And if you factor out an h, what am I left with? Negative 1 minus 3h minus h squared all over h. And what's the good news? I did all of this so I could cancel out the h's. And when I do that, now I know I could, this limit exists. We're not saying that all of a sudden 0 is defined, but this limit exists. Because if you remember, we have an open point here. Now I could use direct substitution and plug in 0 for h. And if I plug in 0 for h, what do I get? I get negative 1 minus 3 times 0 minus 0 squared, which is just negative 1. So what do we just find? We found that basically the slope of the tangent at the slope of the tangent line to this curve at 1 comma 2 is negative 1. So I haven't found the equation of the tangent line yet, but I've done the hard part because the slope is now basically, we could use point slope form. So the slope is negative 1, the point is 1 comma 2, so the equation of my tangent line is going to be y minus 2 equals to negative 1 times x minus 1. This is just a point slope formula of the equation of a tangent line. Now we can leave it at that, or if you want to write it in slope intercept, that's up to you, which would, if I write this in slope intercept form, what do I get? I get negative x plus 3. So let's really quickly verify that this is in fact the tangent to that curve at x equals at 1 comma 2. So let's graph this. So I'm going to use my graphing calculator, and what do I have? We want 1 plus 2x minus x cubed, and the equation of the tangent line was what? Negative x plus 3. So if we graph this, you're going to notice there's the cubic, and there's the tangent line, and there you have it. It's tangent there. Remember, we don't care if this tangent line touches the curve in more than 2 places. See, we care about the short run. Like in this region, that line is tangent to this curve, okay? We don't care about the long run, but in fact, it is a tangent at that point. So if I were to zoom in on this even more, you would see it, which if I come to this part and I zoom in, there's the x cubed graph, and there's my tangent line. So you could clearly see that's the equation of the tangent line, okay? So let's talk about velocities. So here's how we define velocity. So think of it this way. If we're given a function that describes the position of an object, and of course this function that describes the position of the object, it has a name. This is called the position function, okay? Then if we find the slope of the tangent line at a specified point, we are then finding the velocity of the object at that point, which is also, so this is also known as AKA instantaneous velocity. So here's all I'm saying. If you think about it, we're saying there will be times where the slope of the tangent line is the same thing as the instantaneous velocity of an object, okay? But when will that be the case? When the function describes the position of an object. So remember, we're being very, very specific. Now, why is that the way it is? Think of it this way. If I have a curve and I find the slope of the tangent line, what does the slope tell me? What does the slope of the tangent tell me? It tells me at that instant, this is how much that curve is changing by at that instant. So if you think about it over here, if you think about it this way, this is a hill and you're going to go sliding down a hill. If you're sitting up here, what's your velocity going to be? If that's your position, what's your velocity going to be? Your velocity is going to be 0, because if you're sitting on top of the hill, the slope of the tangent is a horizontal line, which means you're not going to have a velocity. You're not going to move anywhere. You're not going to be changing. But if you're here, you are going to have a velocity. Okay, and what is your velocity going to be? It's going to be this pretty much described by that slope of the tangent. It's going to tell you how fast you're moving or you're changing at that instant. So do you guys see how the slope of the tangent line, not only is it a slope of the tangent line, but for the instance where the function describes the position of an object, the slope of the tangent line is also the instantaneous velocity of the object. And see, these are the things that I remember when I first saw calculus, I was really excited about. And I was like, this is so cool, because we're doing things out there that are just like the real world. And so, you know, velocity is all around us, whether you're sitting in a car and, you know, or you're dropping an object. And so we could actually apply these things that make sense and, you know, get so much out of them. So in other words, here's what we're saying. So the velocity of an object at some given value a is simply what? The limit as h approaches a of f of a plus h minus f of a all over h, which notice how this is strictly the same thing that we did for example 1, or when we talked about the slope of the tangent line. However, what's the extra condition? What must f be? F represents the position function. So here's the thing. If we don't know that f is the position function, the only thing we could say is that this finds the slope of the tangent line to this curve f at a, okay? But if f is the position function, not only is it the slope of the tangent line, but that number, the number we get, is actually the velocity of that object at a. Okay, so that's what's kind of going on here. So let's look at an example where we'll kind of put this to use, and then we'll wrap up this section with one last comment. Okay, so for example 2, let's actually start on a new sheet so we have plenty of space. So for example 2, we're going to say the displacement in meters of an object moving in a straight line is given by the equation of motion, which is s equals to 4t cubed plus 6t plus 2, where t is measured in seconds. Okay, so what we're going to say is find the velocity of the object at t equals a, t equals 2, and t equals 3. Okay, so here's the thing. you'll see in a minute why we care to find it in t equals a first. In fact, I actually like this because it looks like we're going to have to do that, perform this process 3 times, but I claim we don't, and you'll see why. So here's the thing. If you look at this function here describes the displacement, which in other words, it gives us pretty much the position relative to where I was at each given time. So it's the position relative to where I started at each given time. So if you think about it, this right here is the position function. So if they want me to find the velocity of this object at t equals a, what does that mean? To find the velocity at t equals a, that's basically saying the same thing as the limit as h approaches 0 of s of a plus h minus s of a all over h. Okay, so let's go through this process. Let's find this out. So then what do I get? The limit as h approaches 0 of s of a plus h, which is 4 times a plus h cubed plus 6 times a plus h plus 2, and then minus s of a, which would give me what? 4t cubed, or sorry, 4a cubed, not t cubed. 4a cubed minus 6a minus 2 all over h. So once again, here's the good news. The 2's will cancel out, okay? And then if I distribute the 6a plus h, what do I get here? I get limit as h approaches 0 of 4 times a plus h cubed plus 6a plus 6h minus 4a cubed minus 6a all over h. So the 6a's will cancel out now. And then it looks like I have no choice but to multiply out the a plus h cubed. So let's just come off to the side and multiply the, so far, here's how much I've simplified this. Limit as h approaches 0, it'll be 4 times a plus h cubed plus 6h minus 4a cubed. Actually, I see a shortcut. We don't need to multiply this out. So I'm going to regroup these. I'm going to regroup it this way. I'm going to put these together. I'm going to factor out a 4. So if I do that, I'm going to have a plus h cubed minus a cubed plus 6h all over h. So what I could do is I could factor this by using the difference of cubes. So in fact, maybe I'll be better off just by cubing this out instead of factoring, just because this is going to get the a cubes to cancel out. So what's a plus h cubed? A plus h squared is what? A squared plus 2ah plus h squared, and then multiply that by another a plus h. So what do we get? A cubed plus 2a squared h plus ah squared plus a squared h plus 2ah squared plus h cubed. So what do I get here? I get the limit as h approaches 0 of 4 times what happens in here. I get a cubed, and then a squared h is, I have 2a squared h, which will be plus 3a squared h. And then I have ah squared plus 2ah squared, which is 3ah squared. And then plus h cubed plus 6h all over h. Now here's the good news. See, and I have a minus a cubed that I forgot. This, don't forget this minus a cubed. So the good news is the a cubed and the minus a cubed cancel out, and I have everything in terms of h's left. So what does this simplify to? The limit as h approaches 0, I have 12a squared h plus 12ah squared plus 4h cubed plus 6h all over h. So you could factor out an h, and you get limit as h approaches 0, factor out an h, gives us 12a squared plus 12ah plus 4h squared plus 6 all over h. So I could cancel out the h's, and the good news is once I do that, now I could plug in 0 for h here. So 12a squared, there's nothing for me to plug in, so that will be 12a squared. And then if I plug in 0 for h here, that zeroes out, and I get plus 6. Okay, now look, 12a plus 6. That's the velocity at t equals a. Now, why do I like this? Because this is saying, now look, you tell me what time it is, I could replace a with that time, and I could give you the answer. So to think about it, if I come back to all this junk, which we did a lot of work, but if you look at this, at t equals 2, I don't have to redo all this work over again. For t equals 3, I don't have to redo all this work over again. All I have to do is come down here, at t equals 2 seconds, replace a with 2. At t equals 3 seconds, replace a with 3. So basically, for t equals to 2, the velocity would be what? V of 2 would be 12 times 2 squared plus 6, which what is that? 54 meters per second. Okay, and then I'll let you do the one for t equals 3. You just literally plug it in. So I like the fact that they say find it at t equals a first, because you're keeping the velocity at each given time very generic. Then it says, okay, well, you tell me then what time do you want? Then you just plug it in for a, instead of having to do this process over and over and over. Okay, so I know it could be a little time consuming, but it's basically just simply working with limits. And if you think about it, our goal is to be able to plug in 0 for h. We first have to cancel this h out. So the good news is we should be able to cancel this h out, and then we could use direct substitution. Okay, so the last comment I want to make here is that instantaneous rate of change. And if you think about it, the slope of the tangent line, as I mentioned, when you have a curve, the slope of the tangent line is in fact telling you at that instant how fast this graph is changing by. So when you see instantaneous rate of change, that's another way of saying find the slope of the tangent line. So instantaneous rate of change is another way of describing the slope of the tangent line. So in other words, for example, the instantaneous rate of change of f of x at a is given by limit as h approaches 0 of f of a plus h minus f of a all over h. So if you think about it, you're like, wait a minute, isn't this the same thing as what we did earlier? And the answer is, of course. So if you think about it, this one simple idea, which is finding the slope of the tangent line, is used to also find the instantaneous rate of change of a function, which is another way of saying slope of the tangent line. And then furthermore, we said, look, if f represents the position of a function at a given time, then the slope of the tangent line is also velocity, okay? And it's also an instantaneous rate of change is also velocity. And in fact, think about it. I hope this makes sense to us. Instantaneous rate of change. Think of it this way. If this is the position function, ask yourself or answer this question to yourself. What is the instantaneous rate of change of position? Right? Or what causes your position to change at each instant? Shouldn't the answer be velocity? And in fact, that's what it is. So instantaneous rate of change of position ends up being velocity. But remember, that's only if you have the position function. The instantaneous rate of change will give you velocity. And any other type of problem, if we don't know what f is, Like, see, if I don't tell you what f is and I say, hey, what am I doing here? You'd say you're either finding the slope of the tangent line, or another way to put it, you're finding the instantaneous rate of this function at x equals a, which is basically saying the slope of the tangent line. Okay, but the only time we could say that the instantaneous rate of change is velocity is when this function is position. Okay, so I hope you're not too confused by this, because there's not much going on here. It's literally we're doing the same thing the same thing over and over and over. It's just in different contexts. Okay, so if you have any questions, feel free to ask. Don't hesitate. But that pretty much takes care of section 7.